Alright, you guys missed it, I know, but we got some more videos, and so I hope you really watch these, pay attention, take the notes. I know some of you actually, I don't know if you want to say admitted to me that you liked the videos, that you liked that you could go back and rewatch them, and that you could watch them before the test, so that you could kind of use that as a refresher. So I'm glad to see that some people out there actually uh, liked the videos. I really do think they will help you in the long run. You just have to give them a chance. You have to watch them. If you don't watch them, you're going to have no clue what's going on. Alright? So, the first lesson we're going to look at today is on simulations. And simulations is kind of like doing an experiment without actually doing it. We're going to pretend that we're going to do something. And we're going to let random chance, primarily with our random number table, kind of make believe different events that could happen in our experiment. So we're not actually going to do like different treatments, but we're going to just do like different scenarios. Like what could happen if you did something over and over and over again. So some different things that you could look at with some simulations, like flipping a coin. What's the chance that you're going to get 3 heads in a row with 10 flips? And this is something we're going to look at in the first example. We could talk about having kids. We could simulate having kids. We don't actually have to have physical kids, but we could let random numbers represent boys and girls. And we could see, over 5 kids, how many were boys and how many were girls. And airlines use simulations quite a bit to try to figure out, they know that not everybody is going to make their flight, so they will oversell tickets so that they're guaranteed that in the long run, that if some people don't show up, then if they sell more tickets than they really had seats for on the flight, they're still going to make their money because then those extra tickets take over the people who didn't show up. Not too often, but it does happen that people will show up for a flight and there won't be any extra seats because they sold more tickets than they really had seats. And it just happened to be that that worked out that way. But airlines use that quite a bit. Now, 3 methods for doing a simulation here. We can try to estimate the likelihood of a result of interest by actually carrying out the experiment many times and calculating the result's relative frequency. You can develop a probability model, which is something that we'll talk about the next day. So you don't quite know what a probability model is yet. And number 3, we could start with a model that in some fashion reflects the truth about the experiment, and then develop a procedure for imitating or simulating a number of repetitions of the experiment. That's what we're really going to be doing here, is we're going to be imitating an experiment through a simulation to see what could happen. Now, we usually have 5 steps here for performing a simulation. We're going to state the problem or describe what we're going to be doing. Sometimes we need to state any assumptions we might have. We need to assign digits to represent outcomes. And we're going to simulate many, many times. Okay? You can't just say, well, if we wanted to have 5 kids, how many boys and how many girls would we have if we have, say, 5 kids, and each boy and girl has a 50-50 chance of being selected, and one child is independent of the next child, meaning if one's a boy, the next child still could be a boy or a girl, 50-50 chance. Now, if we did that just one time, and we had, say, boy, boy, girl, girl, boy, that doesn't mean that's always going to happen for every 5 children. So that's why we want to do this many, many times. And then at the very end, we're going to state our conclusions that we found from our simulation. Now, in the first example we're going to look at, the problem we're going to focus on is how likely is a run of at least 3 consecutive heads or 3 consecutive tails in 10 tosses of a coin. Now, heads and tails are 50-50. And if I said, give me a series of heads and tails that could randomly come up, and more times than not, you're probably going to give me, you're going to keep going back and forth. You're going to maybe go heads, tails, heads, heads, tails, tails, heads, tails. You're going to be just flip-flopping back and forth heads and tails pretty frequently. Well, in real life, heads and tails, there might be 4 heads in a row or 5 heads in a row. And you might think, well, that doesn't really seem random. But it does happen. It doesn't happen often, but it does come up. So first, to kind of describe what we're going to be doing here, we're going to select 10 digits, and those 10 single digits are going to represent 10 tosses of our coin. And we're going to select it from table D, or our random number table. And I've got up here, we're going to use line 105 of our random number table, which I just picked whatever. There's no significance behind 105. And we're going to let our 10 digits represent, to simulate tossing a coin 10 times. And we're going to see if 3 evens or 3 odds occur consecutively. And why I say evens and odds is because evens and odds are 50-50, just like heads and tails are 50-50. And we're going to do this many times. We're not just going to read 10 single digits and stop. We're going to read 10 single digits many, many, many times. And we're going to see how many times 3 even or 3 odd numbers come up in a row. So some assumptions. We're going to assume that heads and tails are equally likely to occur, that they're 50-50. We're also going to assume that tosses are independent. And again, what this means is, if I flip 2 heads in a row, that means the next toss still could be heads or tails. It doesn't mean that if so many heads come up in a row, that you're due for tails. And that was something that you guys read about in the notes that you did the day before, which was the law of averages. Part C, assign digits to represent the outcomes. So I just said I'm going to let evens be tails and odd numbers represent heads. Okay, and you can use evens and odds only for 50-50 simulations. Alright, so now what I'm going to do is I'm going to go to my random number table, which is right here. And I'm starting with line 105, and I'm looking for 3 even or 3 odd numbers, at least that many, in a row out of 10. Okay, so here's the first 10 numbers. So I'm looking for 3 even, 3 odd in a row. And right here, to begin with, there are 4 odd numbers in a row. So that represented 4 heads being flipped in a row. And then I've got a tail. So I mean, I don't have to keep going on here. You know, here I've got 3 tails in a row. But all I was looking for within 10 tosses of a coin was, did 3 heads, at least 3 heads, or at least 3 tails come up? And that did happen here. So I'm going to highlight this green because that happened. So now I'm just going to keep going on. Here's my next 10 right here. So 3 even or 3 odd in a row. There's, how many we got here? There's 6 in a row, 6 odd numbers in a row. So there's 6 heads. So in the next, it happened. How about in our next set of 10 here? So we got even, even, odd, 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 odd. Oh yeah, we've got lots of heads that popped up there. How about in the next set of 10 here? So odd, odd, even, odd, 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 yeah, bunch of odds. So in the first 4 sets of random numbers, we've had at least 3 heads or 3 tails pop up 4 out of 4 times. And you might think, that just doesn't seem right. That doesn't seem like that would happen that often. But it's happening so far. Eventually, we're probably going to run across where it doesn't happen. Okay, so let's just keep going on, and let's move on to line 106. So here we've got even, even, even. So it happened again. Odd, odd, odd. Happened again. Even, odd. Even, even, odd. Odd, odd. So there's odd, odd, odd 3 times. Odd, even, even, odd, odd, even, odd, even, odd. So here it didn't happen. 3 times in a row, at least 3 times in a row, we didn't have 3 evens or 3 odds. So let me grab a different color here. We'll say, finally, out of 8 simulations here, it didn't happen that one time. But let's keep going. Well, I'll tell you what, here's what I'll do. I'm going to pause the video, and then I'm going to keep going along because this is going to get a little boring if you're just watching me highlight here. But I want you to try to follow along, and so you just get practice with it. Or if not, here in a minute here, once I unpause the video, you'll see me doing many more simulations. Okay? So you can either do this yourself, kind of pause the video, or just stay put, and all of a sudden I'll have all these others highlighted in 2 different colors. Well, first I need to get my selector. Okay, here's what I did. I ended up doing 50 simulations of 10 tosses each. So you can see the ones here that are highlighted in red are the ones where I didn't get at least 3 heads or 3 tails within those 10 tosses. And that happened 1, 2, 3, 4, 5, 6, 7, 8 times out of 50. Which means it happened 42 times out of 50. Jump back over here. So got 3 heads or 3 tails in a row. 42 out of 50. Did not. 8 out of 50. So my conclusion is we estimate the probability of a run of at least 3 heads, consecutive heads or tails, and 10 tosses of a coin to be, now this is where I'm going to get my probability from. It happened for me 84% of the time. It didn't happen 16% of the time. So my probability that I would estimate based on my simulations is 84%. Now the whole goal of this chapter is later we're going to do a lot more probability. So the true probability that you don't technically know how to calculate yet is 0.826. 82.6% is the true probability. And how close was our simulated probability to our true probability that you technically don't know how to calculate yet? It is pretty close. So you can see that just using a simulation gets you at least somewhat close to the actual true probability without actually calculating it. Alright, the second example, and I'm going to use line 101 of the random number table, but I'm just going to show you how many trials it took for me to see what I'm going to describe here, because it just takes way too long to run through this. So the second example says, in the game of Scrabble, each player begins by drawing 7 tiles from a bag containing 100 tiles. There are, well, if I can move that over, 42 vowels, 56 consonants, and 2 blank tiles in the bag. About 3% of the time, the first player in Scrabble can bingo by playing all 7 tiles on the first turn. How many games of Scrabble would you expect to have to play on average for this to happen? Design and carry out a simulation to answer this question. So what we're going to do is we're going to select double digits from the random number table to represent whether or not a Scrabble player bingos. We're going to count how many times he plays until a bingo occurs. So basically what we're going to do here, as we're reading numbers off the random digit table, basically the numbers we're looking for, the favorable numbers, the bingoing numbers, is basically only looking at the first turn. So can the player on the first turn use all 7 tiles? If he can, then that's a bingo. If not, we say he didn't bingo, and we would simulate playing another game. We say forget about the rest of the game, we just want to know what happens at the very beginning of the game. Now repeats are going to be allowed here, okay? Because we're not referring to specific numbers from the random number table to represent certain events. Okay, so let me get down here. So when we're going to let 00 through 96 represent not bingoing, because that's 97 numbers out of 100. And the bingoing, we're going to let 97, 98, and 99, because that's our 3% of the time. So if we saw a 97 occur and a 98 or another 97 occur, that just means that that player bingoed 2 times. Okay, so 97 doesn't refer to a specific bingo, but just that they did, in fact, bingo. Some assumptions. Let's go back up here. A player has a 3% chance of bingoing in any given match, because we were given that information up here. The chance of bingoing is independent for each match, which means, again, that if you bingo in one game, that means you still have a 3% chance of bingoing the following game. You know, you could bingo 2 times in a row. That's not going to happen often, but it could happen. Okay? So, if I were to use line 101, which is what I did here, and I only did 5 simulations, 5 trials, until I found the numbers 97, 98, or 99. Okay? So I started at line 101, and I kept reading double-digit numbers until I came to a 97, 98, or 99. And the first time that happened, it took me 26 times before I found a 97, 98, or 99. Then from that point, I continued on, and I'm looking for another 97, 98, or 99. And it took me 61 times, 61 games, simulated games, before I saw another bingo. And after that, it took me 21 times before I found the next one. And then it took me 49 times to find the next bingo. And then it took me 33 times to find the next bingo. So on average, the player can expect to play how many games before he bingos? All I did to figure that out was I took these 5 numbers and I figured out the mean of them. Okay? Typically, you would probably want to find the mean of more than just 5 simulations. But since it took me so long just to do these 5 simulations, we'll just go along with this. What this means, though, is that the number I'm going to come up with could be further away than the actual theoretical number. Okay, the actual kind of probability that we looked at in the first example. So if I take the mean of all these numbers, I get 38. So just based on 5 simulations, the average time or the average amount of games played before a player would bingo would be 38. The theoretical number is 33 1/3. And again, we'll get to some point, I don't necessarily think this chapter, because this isn't necessarily probability, but we will get to where we will calculate this theoretical number. Okay, now my 38 games, somewhat close to my 33 1/3 games, and you can't really play a third of a game, but this is the theoretical number, not the actual number. So we're not going to round it. Okay, now if you were to use some other line of the random number table, would you come up with these same 5 numbers to get 38 in the end? No, you probably wouldn't. Okay, does that mean that the line you picked off the random number table is wrong or it's off? No, it was just random chance that that's the number that you got. Okay, so chances are what I should have done more than anything was done maybe like 50 simulations and then took the average. And if I took the average of my 50 simulations, my 50 trials, then the number I would get here would probably be much closer to this 33 1/3. Okay. So here's one of the last things we're going to look at. Okay, and this is often the hardest part of a simulation, is assigning the digits to the outcomes. So number 1 here, choose a person at random from a group of which 70% are employed. Okay, now one thing I notice here is this 70%, that it is a multiple of 10. So I don't necessarily have to use double digits here. You could use double digits, but anytime that you can get away with single digits, it's going to be much easier to do the simulation. So I said, what if I let the numbers 0 through 6 represent an employed person? Because 0 through 6, there are 7 numbers. And for unemployed, 7, 8, 9, there are 3 numbers out of 10. So 7 out of 10 is 70%, and 3 numbers out of 10 is the 30% for the unemployed. Now you could have done 0, 0 to 69 and did 70 to 99. Okay, you absolutely could have done that. But if you can read single-digit numbers over double-digit numbers, you're going to be reading, less numbers over time. So either one would technically be correct, okay? But this would be the much shorter way, using the single digits. Now what if we looked at the same